almost match it between 2 points. Some point here, x on the axis, and another point, a distance h away. So this point here would be x plus h. Yeah? That means I could say that the run, at least, is the distance h. The rise, a little bit trickier, but I've called it this. Another word for y is fx in general. This is this function, but let's just talk in general before we specify what a function. We'll talk about in general. To get the rise, I would need these two y values subtracted from each other, wouldn't I? To get the rise of this triangle, so rise over run. This is run, this is rise. So if I knew this number, took away this number, I would get the rise. Now for all functions, if I just sub in x into the function, I will get the y value. So this one would be the function with x subbed in, whatever this one was. And this one up here will be the function with x plus h subbed in. So if you're using x is 2, and this function, you would say this was 2 squared, and this one is 3 squared if h is 1. But we're not. We're saying for every function in general, any function with a curve. So it is the bigger one, take away the smaller one. And that's the rise over run. Right. Now the concept of a limit comes into effect here between when we're trying to get this as accurate as possible at one point. And to make it as accurate as possible at one point, we need h to be what? No, approach 0. So to be as close as possible to 0 without actually being 0. So these 2 points, if we zoomed in, we want to get them really close together. They want to be like this, as in the h distance wants to be tiny, so we can get like an instantaneous gradient. If this line was smaller and smaller, it'll come to such a length as just a point, really. So that's the concept of a limit. We're saying it's not 0, but it's pretty much 0. Okay, let's do this specific example, x squared. So the function h will just be on the denominator, and the function with x plus h in it will be x plus h squared, and then minus x.
Are you making a triangle?
Squared. Here? Oh. I made a rise over run triangle, yeah, but I'm just looking at the rise and the run separately as a fraction. So the run is h. It's going to be h. And the rise is, well, I'm now using this function, the x squared function. So I'm putting in x plus h into x squared, and I'm putting x into x squared. Right. And I get x squared plus 2hx plus h squared minus x squared all over h, which can tidy up a little bit because I think these x squareds cancel, don't they? Then I can divide h into a few things. So I get, I'll just put it up here. Yeah, I get 2x plus h, because the h divides into this, and will disappear from the denominator. And this is where I was saying, right, this works best if h is pretty much 0. We get instantaneous gradient as the limit of h approaches 0. Not h isn't 0, it's just so insignificant. The distance between these 2 points is so insignificant that it's pretty much 0. Which means as h goes to 0, this becomes irrelevant. And the gradient at any point along this line is 2 times x. Gradient at any point along the line. Now some terminology here. If my original function was fx, which it could be, the gradient function is called 2x, or f dash x is 2x. This, terminology-wise, is the gradient function, but you'll probably hear it called more often the first derivative. I know, the sideways. First derivative, or gradient function. If the terminology was y equals, which I started up, y is equal to x squared, the terminology is a little bit different. dy dx, which means d for delta, which is this symbol, delta y over delta x. The change, delta means change. Did you see that in science? The change in y over the change in x, which is just, the change in y was this distance, which is the rise, over the run. The change in the rise over the change in the run. That's delta y over delta x. That's what that means. So this is the terminology if it's just using y.
So, for what's on the board,
Oh, yeah.
called x's.
Well, that's what we're going to come to in a second, using the concept of a limit. But this is the main purpose of the concept of a limit for this unit is, well, not the main purpose, one of the purposes is thinking about what it would, well, the answer would be as it goes towards, but not quite. Is it going towards something, but not reaching it, in another way? It's a bit like when you are crossing the room, what's the limit? If you're halving your distance every time, that one, the geometric sequence, what's the limit of that sequence? Let's say halfway across the room is 10 meters, and then I walk another half, so that's 5 meters, and I keep this pattern going, 10, 5. We used the limits to get what that would add to infinity, didn't we? Even though you just used the formula, but it was an idea that if we went on and on forever, the fractions would get so small that they wouldn't really matter, and you'd be getting as close and close. What number is this one getting close to?
0.
The total distance.
Oh.
10, 5, 2.5, 1.25.
10 over half.
Yes.
10 over half. No?
Yeah, so if half the distance across the room was 10, you'd probably get there pretty. Half the distance is 10. It's going towards. It's going towards 20.
Yeah.
Okay, yeah. So the other half, you go half is another 5 meters, and then 2.5 meters, and then 1. You're almost getting to 20, but you're never actually getting to 20. But you are getting to 20, and that's the concept of limit. You don't get there, but you're going there. We pretty much say that we're getting there. It's exactly what you have to think about for the starter question. So in the starter, we had to look where these functions are going to as x approaches infinity. So we have this first one. As x approaches infinity. Okay, so one way to think about it is sometimes you just sub in the value. And we looked at this on Thursday, where we sub in the value, and what happens here? We get 3 times infinity minus 2 over infinity plus 1. Is that...
You take x plus 1.
Well, then we can think about our knowledge of this type of function.
That the asymptote's minus 1.
There's an x asymptote at minus 1. What's the y asymptote? Can you remember?
That's such a great question.
3x minus 2 equals to 0.
No.
3 by 1.
Yeah, it's 3, isn't it? So what does that mean? So the x asymptote is minus 1, isn't it? So that means it's like a dotted line here or here at minus 1. And we at 3, wasn't it? The coefficient here, coefficient there. So is that 3? What shape has this function got? Does anyone have an idea?
Oh, like those two.
Is it this one?
Yes.
Yes.
It's those little corner things.
Okay, it's going to look something like this. So, and then this question is asking, as x approaches infinity, as x goes towards this way, what number is it going towards?
3.
3. Will it ever reach 3?
No.
No. What happens if x was 3?
Then it
Or
would
sorry,
be
if y was 3?
undefined. The limit does not exist.
No, the limit,
That is the
this is,
3.
It's exceeding its limit. It's about a worse.
that's not going to, yeah, it's not
You
going
always draw it.
no, you don't have to always draw it. No.
How would you do it?
Because you know the asymptotes. An asymptote is a line that is approaching. It can cross it in some stage, but But as it goes towards infinity, it's approaching it, or goes toward, yeah.
So what is 3? What did we just find?
The limit of this function as x approaches infinity is 3.
So you just write it as equal to 3.
Yeah, the limit of the function, yeah. That's what this question is asking. Okay? Now limits don't really become that important until later on. We don't really think about it too much when we can come back, and as Aidan mentioned, stuff like L'Hopital's rule and stuff, which is further down the system. But the key feature of limit that we needed to look at was this one, h approaching 0. This distance cannot be 0, because then we'd be just dividing by 0. We don't want that. But it can be as close as possible to 0. So these two get closer and closer together, so they become an instantaneous gradient at that point. And that is what this is about. And when we get a derivative, we get something called the gradient function. It tells how steep the function is all along it. So when x is, and we can see it here, when x is, let's say when x is equal to 10 here, further down the line, it should be pretty steep. And it is the exact steepness of 20. The gradient is 20 when x is 10. The instantaneous grade is very uphill. And when it's -5, the gradient's going to be -10, which makes sense because this is going downhill at that stage. And what's the gradient at 0?
0.
0. Flat. It's flat here, and then it starts to go uphill, 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 and will go uphill forever, 2 times whatever the x value is. And when it's backwards, it's all going to be downhill before it hits this spot, so they're all going to be negative gradients. Yeah.
Would that formula work for more, for every single function, or just x squared?
It will work for every single function. So let's do another one. Let's do a much more difficult one. And let's see how we get on. So this is called from first principles, deriving from first principles. There is a shortcut, which we'll get to in a second.
Wait, do you have to know how to derive from first?
Like, will the question ever ask you, like, state derived from? Boy,
Possible.
you're so unserious.
I think for first, I think it's only ever been asked once as far as I can recall
Like
So
in the actual
in the actual exam, yeah.
like you probably won't, add it.
Probably not. But anyway, let's learn how to do it. Let's, I think I might have put an actual, I'll do a,
Yeah, I'm gonna put the one question that they've ever asked on there. Yeah.
okay, let me, I have one lined up, so I'll just do that one.
My mistakes are you.
just like your French song.
Okay. So I'm going to do the harder one of these. Oh, I don't want to do the cube one.
The first one looks easy.
So do the second.
It's like the first
Let's do the second one. Okay, I'm going to do the second one here. So you see how find the change in y over the change in x from first principles. So we got this second one here. Y is 2x squared plus x minus 1. Okay. So from first principles is I'm going to look at the rise over the run. So the limit when h goes towards 0, so when this distance is as short as possible of this function, the run is easy because it's going to be h. The rise is going to be x plus h subbed in minus x subbed in. So let's do x plus h subbed in minus x subbed in, which is just going to be minus all this. X squared. Okay? So this is what's going on over here is the function with x plus h put in, take away the function with x plus in all over h. Same thing here, just getting the difference between this and this all over this distance. The rise over the run. Delta x over delta, or delta y over delta x. Change in y over change in x. So this is just an algebra problem. Just multiply this out, which is a bit of a pain, but maybe we do it in one go. 2x squared plus 4hx maybe plus 2h squared. Have I done that right? plus h plus x minus 1 minus 2x squared minus x plus 1. The minus affects that there, all over h. A few things probably will cancel out here. 2x squared, x, x, minus 1 plus 1. H divide into everything then to give 1 in the denominator. So that gives 4x plus 2h plus 1. Happy with that?
Yeah.
Okay.
Wait, but where did the x over h disappear?
X over H.
Oh, wait, no. Never mind.
Okay.
Cancel it.
And then we apply the limit now. We apply the limit. Limit as h approaches 0, so as h gets to nothing. That goes away then, doesn't it? It's nothing.
Oh.
So we get 4x plus 1 as r. That's the gradient function. It gives me the gradient anywhere I want along this function.
What is the first? Where did you get +1 from?
This is from first
Is
principles.
that your final answer?
This is it. Doing this minus this over h, and then looking at h going to 0. That's first principles. So you,
Why do they call those equations first principles?
they haven't. They've defined find the derivative from first principles.
Isn't there?
Functions that we have to find.
They're just random functions. You use anything.
But is that it then? Or would
That's
it
it. Yeah. This is the change. Now this is the change in y or the change in x. Yeah. This is the answer.
And for y equals x squared, would it be 2x or just 2?
2x.
2x, not 2.
Now, that is definitely the long way.
Is that the easier way is with the powers?
Short way, called by rule. Now, I know a few of you know how to do this, so don't spoil it. Don't spoil it. Don't spoil it. Okay, over here, I'm going to write the function. And over here, I'm going to write its derivative or gradient function. And let's see when any aha moment comes in. So the first one we have 2x squared plus x plus minus 1. Yeah, that's it. And its derivative is 4x plus 1. So hint here, if this is your first time seeing this, you can do it by just looking at the function. 6x5 minus 7x cubed plus 2x. You'll be able to do it in a second. The derivative function of this is 30x4 minus 21x squared plus 2. All right, I'll do another one. 12x cubed plus 17x squared plus 6. 36x squared plus 34x. You got it? Charlize? Almost? Yeah, you got it? Yep.
Wait, I'm clocking it. Yeah, I see it. Okay.
Okay, so this is something called the power rule that works for polynomials. Most people saw it within a couple of goes. So 5 times the power times the number in front
And then minus 1.
gives this number, and then take away, and then repeat. What happens any constant? Like 6. Bye-bye.
It's 6 to the power 1 minus 1. So it's oh, wait, no. It's like in respect to x, and they don't got an x, so they're not invited to my club.
Well, why does it go away if you think about what we just did?
Because it cancels out.
It cancels out, yeah. The one here cancelled out with the 1, and then there was not left. This 1 came from the x, actually, didn't it? Because they h here.
What was the formula for the right one again?
For this one?
Yeah.
It will always be the function with x plus h in it. Take away the function with x, all over the h. Limit as h goes to 0. So this is the rise over the run. The rise over the run. This is first principles. Okay. Let's give you a bunch of these. See, can you... Why?
Interesting.
Oh, which
Oh, yeah.
ones?
Wait, what does it mean with differentiate?
Right, so now we are at the stage of this process from here to here is the first derivative, which is differentiation. So differentiate, or get the first derivative function, the gradient function for all of these. So you can definitely do question 1 here. Question 2, so the power rule is, if here's a number, if we have this, we do, what is it? Take away 1 from the power and multiply down the old power in front. This is called the power rule. Now it only works if it's written like this. Like, you won't get cosine x written anywhere here. It's only a polynomial like x to the power or something. What happens if I have 1 over x squared, or cube root of x?
You would change the n to...
Turn it into a power as we know it. This would be x to the minus 2, and this would be x to